Yes.
Okay.
Yeah.
Must have kept it coming.
Yeah. So this is
I hope so.
into the black box. At least.
I should go find Robin. I know he was asking,
I
and
know,
then he
yeah,
kept on
it's
asking
true,
about
yeah.
this.
All right.
Yeah, pick up issue. Yeah.
Sorry.
So way back, we talked about Bayes' theorem, and we talked about the idea that in terms of math, we can talk about the probability of the parameters, where theta is like just a representation for all the parameters in a model, given the data, is equal to the probability of the parameters, which is the prior. So probability of parameters regardless of the data, times probability of the data given the parameters. And then all that gets divided by the probability of the data. You'll have to just trust me that you actually can just ignore this bottom point. The background on that is, I guess, just really quickly, is that for a given question, you're going to have the same data when addressing that question. So if you're asking about what are the relative probabilities of different values in theta, well, this formula for a given value of the for a given data set is just going to be well, you're going to have the same thing at the bottom. So if you're comparing what is the probability of a theta value of 0.1 versus probability of a theta value of 0.3, the top bit changes because you might have a different prior for those 2 points, and the likelihood, this bit over here might change depending on what those 2 points are. But the data stays the same regardless of what part of the parameter space you're talking about. So for a given data set, you don't actually need to worry about this bottom part. Everything's just, you're talking about in the parameter space, what are the high parts of the curve and low parts of the curve. You're not actually ending up getting out the absolute probability. You're getting out what's called a, what do they usually talk about it? A constant ratio, or what is it? There's a mathy phrase for saying you don't need to worry about the bottom part. They talk about it up to a constant. You can work out the probability of blah, blah, up to a constant. Anyway, where the data would end up influencing what the constant was. So if you changed your data, you'd need to change your representation of the posterior by multiplying by some constant that's determined by whatever that probability of the data is. And we don't need to. We never do that anyway, so we don't need to worry about that. So we've got this formula where we talk about the probability of a given value for the parameter, or a given point in the parameter space, given the data, is equal to the probability of that point in the parameter space times this thing over here. Now this thing over here, the probability of the data given that point in the parameter space, that's another name for that is the likelihood. So we'll talk about P of theta is the prior, and P data given theta. You'll hear this spoken of or referred to as like, and then I always don't know. No, there's no E. Likelihood.
What?
What, you think there's an E?
No way.
No.
I don't think at all right now. So
Yeah.
No, there's an E.
There is an E.
There is an E,
Yay.
yes.
But maybe that's American, I don't know.
Yeah. Okay, likelihood. So what we need to do to work out this Bayes, the posterior for a given data set is, and a given model structure, is to simply figure out what this likelihood is, figure out what the prior is, and multiply the two. So you'll see a lot of examples online that talk about the binomial example, which I actually find is a little bit weird because we then most of the time talk about Gaussian data and that sort of thing. So let's start with the Gaussian model. So the model is that the data is distributed as normal with some mean. And let's go way back to like our first day and talk about that z-test scenario where we will know what the distribution is for the data. So maybe I'll say, you know what the noise is for the data. So I'm going to do inference on this model where I say the data is distributed as normal. I'm uncertain about this mean here. Maybe I'll call it mu. But I am certain about what this standard deviation is. It's 15. So I then go and I observe some data. So I go and I observe some data. Let me put some numbers on this. So let's say it's this IQ example. And it's justifying this 15, this assumed standard deviation of 15. So I get 100, and I'll put n points. So this is maybe 120, and this is maybe 80. All right, and I observe a value right here. Frequentists, you're not going to be able to do any inference on that. There's no mean. There's like well, actually you would. Yeah, you just to get the z-score for that. So ignore my derision of frequentist just there. There's better points of derision on frequentist stuff. Okay, so I observe a value there. So what I need to do is figure out two things. First of all, I want to translate this observation to, I'll put two more curves down here. I'll have a prior and a posterior. All right, so before we even saw the data, let's pretend we didn't see the data yet. We'd want to establish a prior on mu, which presumably would be sort of somewhere peaked around 100, tapering off on either side if we were to ask ourselves about each value. And we can simplify that by expressing that as sort of a normal distribution. So I'd be not very surprised if I were to eventually find out that the true value was 100. I'd be very surprised if I found out the true value was 120, and very surprised if I found out the true value was 80. Not very, reasonably surprised with it if it were like 105-ish, which is around right there. So that's pretty straightforward. You guys are pretty familiar with these prior distributions. So the question is, how do we combine the data point with our model and this feature of the model, which is our prior on this parameter of the model, to establish our posterior? So for each, again, possible mu value, what should we believe about the credibility of that mu value? All right, so what we do, we start plugging away guesses at what mu is. Okay, so let's say mu is 100. Well, if mu is 100, let me actually get a second piece of paper to start writing these things down on. Yeah, I guess this is a good reason to have the widescreen format for the. So if mu is that, the p, what is our prior at that point, and what is our likelihood at that point? All right. So let's choose, oh, and one other thing. So I told you we'd establish a form. We'll use a Gaussian. Let's actually express what that Gaussian is. So it's normal with a mean of 100 and an SD of what? What do you guys want to have as your standard deviation?
15.
That might get a little confusing with the 15 that we're assuming in terms of the distribution of values across the population.
Also,
Yeah, let's go with, I heard 8 there. Let's go with 10. It looks kind of like it's around 10 or something. All right. So let's establish that our prior takes this form of a normal distribution. You could actually have the prior take any shape you want as long as you can actually express for any given point what the height of the curve is at that. We have nice built-in tools to express that for a normal, so that's why we use that. There's some other mathy reasons to do that, to use a normal. With Stan, I'm not sure.
I was about to say, I thought we had done non-normal priors.
Yeah, so we've done Weeble.
Right.
We've done some, but like, I'm thinking like a prior that has like a really weird
Not even like an internally
bimodal or
non-parabolic shape.
I think they do have to be continuous. So infinitely differentiable, I think, is a word for that.
Okay. So you mean not even like normal, as in like, you know, what you would just
Standard.
call it a normal distribution, normal like I don't even not weird.
Yeah,
say.
exactly.
Like,
Okay, so given this model specification that the data have a normal distribution with some unknown mean but a known variability, and a prior on the thing that we're uncertain about, the mean, we can start stepping through a variety of guesses for what the true value of mu is. So if, say, we said, a value of mu of 98. Well, the first thing to do is figure out what is the probability of mu at 98. So we'd look at our graph for the probability, and we see, okay, here's 98. Let's go up until we find 98 and find out what is the height of the curve at 98. We can do that easily in R by, I'm going to do a new session, just so we don't have all this clutter. We won't need any of that. Okay. So we can easily do that in R by doing d norm. D gets the height of the density curve at a given point. So where's our graph? So we want the height of the points when mu is 98, but the standard deviation is 15. So 98. Yeah. Sorry. See, I'm even confusing myself here. So we want the height of this curve, i.e. when it's a curve that has a mean of 100, a standard deviation of 10, at the point 98. So put the point on the x-axis you want first, then you put the mean and the standard deviation of the curve. So 0.4-ish. All right, so I'll put 0.4 there. All right, next we need the likelihood. So that is the point on so our guess for mu was 98. So we can draw a curve on this graph corresponding to a peak at 98. But again, with a standard deviation of 15, poorly drawn here. Given that guess of a peak at 98, we can express what the height of the curve is over this data point. So going back over, we'd say d norm, and the data point, say this data point is 103. So we'd say the height of the curve for 103 given a mean of 98 and a standard deviation of 15. About 0.25. So we can plug in 0.25. 0.25. There we go. And this is 0.04? Yeah, 0.04. All right. And from that, we can actually work out what I didn't leave myself enough space, but the thing we're actually interested in, which is the probability of theta given the data, is just the multiplication of these two numbers, 0.04, 0.025. Times 0.025, 0.000. So that defines
Two zeros, up 3.
yes. So that defines on this curve for a value of 0.98 the height of the curve, how high it should be.
So then it just does that a whole bunch of times.
And you just keep doing that a whole bunch of times. So let's choose another value. Let's do 102. So we'll work out what is the height of the curve for the prior over 102. Again, so 102 is going to be somewhere around here. So what is the height of that curve? So this is our prior curve with a mean of 100, standard deviation of 10. Instead of 98, we'll look at 102. Should be the same value because it's 2. 98 was 2 down from the mean. 102 is 2 up, so it's 0.04. Now the probability of the data given that mean, again, is the height of the curve such that we peak it at 102. So it's peaked around here, but it still has this standard deviation of 15, so it goes, bad drawing. But what is the height of the curve now? So we can figure that out by looking at 103 when the mean is 102 and the standard deviation of 15. So 2.65, so let's round up to 2.7. Or 0 to 7. Multiply those out, and that gives you some number that presumably is a little bit bigger than this number. So 102 is a little bit more likely as a, or is more credible as a value than, let me actually do it. So 108, there's no way I'm going to be able to actually show that. But a value of 102 is going to be slightly higher than this one. Once we get all the values out, you rescale so that it sums to 1 anyway, so that you can talk about it as you just rescale it till you can see it better. But if we were to continue to do this all along the number line, we'd eventually get out a posterior distribution that would be, we only have one data point, so it's not going to move very far from our prior here. So it's probably going to be, if we scaled all these up, something, I don't know, like that. A little bit tighter, moved over a little bit towards the data point that we have, but still fairly close to the original peak. So that's the example for the the z-test scenario, where you are certain about what this parameter is in the model, and so you're only really doing a one-dimensional model where you're moving along this line and figuring out for a given value of mu, what do we get for the prior, what do we get for the likelihood, multiplying those two things to get out what the posterior is, again, on mu. However, let's imagine that you have a model where you say the data is distributed as normal with some unknown mean, but also an unknown standard deviation. So we can express our prior for the mean. And I'll just shorten that to, again, we'll keep it in the IQ world where we can talk about priors based on what we actually know. So peaked at 100, tapering by about 10. We can talk about the prior for the standard deviation, maybe Weibull with a shape of 2 and a scale of, well, if 1 is peaked at 0.8, maybe if we put it a scale of 20, that should be peaked around 18-ish, but still have a lot of mass, a lot of spread in the mass. So we'd have a prior for each one of these. And if you think about, we actually were able to draw out our prior for mu. We could draw out our prior for sigma. But in actuality, we could draw out like the, in actuality, this model is expressing a two-dimensional surface. So if you imagine the potential values for mu being sort of along this axis, and the potential values for sigma being along this axis, each point in this space corresponds to a possible value for mu and a possible value for sigma. So this would be like a value for sigma that's, if I put numbers on this, that was like, well, it's bounded at 0, and it can go up to infinity for sigma. And mu goes from positive infinity to negative infinity. Let's take a little window that's maybe going from 120 to 80. And for sigma, let's look at a window that goes up to, I don't know, 30. So maybe this is, try not to scale, but maybe this dot corresponds to a value of sigma of 1 and a value of mu of 82. So you can express by combining, if you are expressing a prior that we have been using so far of independent priors, you can work out what the prior value is for that point by simply multiplying the two, what the height is for the Weibull curve is, and what the height is for the normal curve is. So in theory, the prior expresses a surface across this space, but it's going to be higher in this plane because it's right in the middle of our so it's going to have sort of a Gaussian shape this way, but then also a Weibull shape this way. So higher values around right here for the Weibull and tapering off. This is where me having an actual graphic that shows that, i.e. like a little heat map, would be ideal for the next time I go through this. But can you see how you can actually express again that there's this bivariate space that establishes our prior? You can actually have a literally bivariate prior where it sort of establishes some sort of correlation amongst the parameters if you had the expectation to have that correlation, but we typically haven't bothered with that. But again, once you sort of see that that we've changed to now a bivariate space, the way of doing inference given a data point, so if the obs equals 103, is to simply iterate over steps through this space in the same way that we did when we simply had a one-dimensional space to search. You choose a point which establishes your kind of guess for what the mu and sigma is. You establish, okay, given that mu and sigma, what is the height of the surface here in our prior? And that gives you, we're no longer talking about the prior on mu, we're talking about the prior on theta, which is the combination of the guess for both mu and sigma. So we get the height of that surface at that guess. So if we were like 90, I guess we'd have to say what theta was here. So it would be two numbers, 98 for the mean and 4 for sigma, for example. So we get a height for that surface at that bivariate point. We then would also work out, given a normal distribution with that mean and that sigma, what does the model actually say for the curve that normal distribution would have? So it would be something like, again, so if this is the data, 100, and there's an observation at 103, and if we're saying it's mean of 98 and standard deviation of 4, it's probably going to be something that looks pretty narrow like this. So 103 is not going to have a very high value. If we jump to another part of the parameter space that had the same mean but a much wider variability, then this peak drops a little bit, but the side comes back up. That's a terribly not normal looking distribution. But so for a given value that's farther away from the data point, increasing the standard deviation will increase its the height of the curve above that point. But as you move the data point towards it, that also increases the height. So there's like a trade-off between the standard deviation and the value for a given data point. So, but what you're actually doing is still the same as before. You're now jumping around, instead of a one-dimensional, you're jumping around a two-dimensional space and figuring out, okay, what's the height of the prior curve for that space? What is the height of the curve that we're expressing for the sampling of our data at the data point given those two parameter values, multiplying those two out, and that gives us the height on the posterior surface. Now, this is already a lot of computation to step through. For a simple model like this, we can actually work out, there's analytic methods to work out the like what the given a given prior in data, and model what usually if you're assuming normal, what the posterior shape is, what the distribution is. You don't actually have to step through and sample all throughout this window. But for higher dimensional models, i.e. you not only have, well, with all the models that we've been doing more recently with the hierarchical, you have like an intercept per person, a variability across people in the intercepts, an overall mean for the intercepts. You have a huge amount of parameters. And so for each parameter, that adds a dimension to the search space. So you're not going to be able to just sample evenly across that search space to reflect the final posterior distribution across that space. You have to actually you have to come up with some other strategy. So I'm not going to tell you anything about that extra strategy, except to say that there's a strategy whereby if you follow a set of rules you evaluate the posterior at a given point, but then where you choose next as your guess follows a specific set of rules, you can guarantee that after you've jumped a while, subsequent jumps, if you keep a list of where you've been in terms of your jumps, like you don't actually keep a record of what the posterior was at that place, but you keep a record of where you've been, that list of where you've been is as if you actually had the posterior distribution and sampled places proportional to the height. So it's as if you had the posterior and you're sampling from the posterior, just like we can ask R to sample from a normal distribution, give me a random normal sample. We can ask, we can imagine that list of locations we've visited recently actually is a list of samples from the posterior distribution. That's why I've been telling you that you can work out in these examples like what the shape of the curve is. But when we actually do Bayesian stuff, we're getting just a bunch of observations along this, which tend to cluster around here, and then they peter out. And so we do things like, okay, well, we'll compute an artificial density around this, or what's the mean and the median, what are the descriptive samples of these samples. That's because we're using this other way of exploring the parameter space where we are not trying to characterize the height at each point and do that across the entire surface of the space, but we're actually keeping a list of where we've been as we've searched in this rule-based way. So yeah, that turns out to be a really good solution to, again, the problem if you did this strategy of trying to, even in the one-dimensional case, you can see that you'd have to, like, in order to get, like, the full characterization of this curve, you'd need to sample an infinite amount of times across this curve. You can start approximating by saying, okay, I'm going to have 100 points along this curve, and that should give me a good characterization of the shape. But as you get more and more dimensions, 100 samples starts to become the same computational complexity, but far more sparsely distributed points across this potential space. So for a given amount of compute power, as you increase the dimension, you are getting less and less information about what the posterior looks like. So yeah, for high dimensional problems, you simply can't use a direct approach to computing what the posterior is. You have to do like this quasi-random exploration through the parameter space. But there's good math establishing that if you do that for long enough, you can treat your history of exploration as itself a sample from the posterior. So it's a really neat realm. Yeah, it's a little mind-blowing. I certainly haven't had the guts to try to delve into the math of that and the proofs, because there are like literal mathematical proofs that as long as you meet these certain conditions, you're guaranteed, if you search for long enough, to be sampling from the posterior. It's pretty amazing. When you think of like some of the models that we have are going to have hundreds, thousands of parameters. So that's thousands of dimensions of space that it's searching through, but yet you're still able to sample from it effectively. All right, I'm going to cut her off there.